Hello students, this is my second lecture on PDE and today we shall discuss solution of PDE of first order and especially for Lagrange's linear equation. Solution of PDE. A solution of a PDE is an explicit or implicit relation among the variables of the PDE, of course, which does not contain partial derivatives and which identically satisfies the PDE. Identically satisfies means the PDE is satisfied by all values of the variables in a certain region. In some simple cases, a solution can be obtained immediately. For example, consider the first order PDE del u by del x equal to x square minus y square. U is a function of x and y. The solution of this equation is readily given by just integrating u equal to integration x square minus y square del x plus 5y. Here, integration x square minus y square del x indicates a partial integration with respect to x, keeping y constant. And instead of c, we have written phi y because the constant of integration may involve y, because in this process we have assumed y constants. It may be phi sin y, cos y, log y, like that. So phi y written. So x square integration x cube by 3 and y square is constant, so it is only x y square plus phi y. So this is the solution. Number 2, if the PDE is second order PDE del square by del x del y, x cube minus 3y square, here it can be written as del x of del u by del y. So it again integrating with respect to x partially, keeping y constant, we get x cube integration with respect to x will be x to the power 4 by 4 and 3y square constant, so only x will be coming plus phi y, because constant of integration is here replaced by function of y. In this process, y constant. Now this is del u del y. So now again we integrate partially with respect to y, keeping x constant. So del u del y will give us u, and x to the power 4 by 4 will be constant, and integration del y will be only, that will be y, and 3x will be constant. Y square integration will be y cube by 3, but this cancels, so it is xy cube plus integration phi y del y plus psi x. So, and this integration phi y del y let us write as gy, and psi x is arbitrary function of x instead of arbitrary constant. So this is solution. So from these two examples we note that we note that whereas ordinary differential equations have solutions involving arbitrary constants only, PDE have solutions involving arbitrary functions also. In general, a PDE may have many solutions. This is another fact. For example, u equal to x square minus y square, u equal to e to the power x cos y, u equal to sin x cos hyperbolic y, u equal to log x square plus y square, which are entirely different from each other as functions, you can see. But they are all solutions of the PDE del square u by del x square plus del square u by del y square equal to 0, two-dimensional Laplace equation. This is known as. And it can be easily verified. Let us verify only this one. Say u equal to sin x cos hyperbolic y, then del u by del x is sin x derivative is cos x, y is constant, and del square u by del x square again cos x derivative is minus sin x. Now del u by del y, cos hyperbolic y derivative is sin hyperbolic y, no minus sign, and del square u by del y square, sin hyperbolic y derivative is again cos hyperbolic y. So del square u by del x square, del square u by del y square, when added we get 0. So satisfies. Similarly, others can be verified. And here we note that derivative of cos hyperbolic x with respect to x is sin hyperbolic x, no minus sign. Derivative of sin hyperbolic x is cos hyperbolic x, no minus. And this is used here while differentiating cos hyperbolic y or sin hyperbolic y with respect to y. We shall see later that the unique solution. Here we have seen 4 solutions of the same PDE, but generally we seek unique solution. So we shall see later that the unique solution of a PDE corresponding to a given physical problem will be obtained by the use of additional conditions arising from the problem, such as boundary conditions or initial conditions. Solution of PDE by direct integration, as in the syllabus. Here we consider such PDE which can be solved by direct integration, as we have seen 2 examples above also. Instead of using constant of integration, we shall however use arbitrary functions of the variable which is held fixed. This is the process. Solve del square z by del x del y equal to 18x square y plus cos twice x minus y equal to 0. Here this can be written as del x of del z del y and rest as it is. Now integrating this with respect to x and keeping y constant. No z is involved here, so we can integrate. So this is del z del y, integrating with respect to x, del x will go. And here x square integration x cube by 3, and cos twice x plus y integration is sin twice x plus y with a half. And in the right side, instead of constant of integration, we have written phi y, because that constant may involve y. So phi y is any function of y only. Now again we integrate this line with respect to y partially and keeping x constant. Del z del y will become z, 6x cube y, integrating with respect to y will become y square by 2, this y, and sin twice x minus y integration will be minus cos twice x minus y, and with a minus 1 because coefficient of y is minus 1. And in right side integration phi y del y plus psi x. Why psi x? Integration constant of integration is here psi x, arbitrary function, because in this process we have kept x constant. So this is this integration phi y del y, let us write as fy, so which is required solution. Now example number 2, del cube z by del x square del y, third order partial derivative, mixed third order partial derivative, is equal to cos 2x plus 3y, integrating with respect to x partially. If we integrate with respect to x, this del x square will become del x only, and this cube will become square. So del square z by del x del y, right side integration with respect to x, cos 2x plus 3y integration is sin 2x plus 3y into half, coefficient of x is 2, plus phi 1y, arbitrary function, because y constant under this integration. Again integrating with this partially with respect to x, we get this del x will go, it will be only del z by del y. So sin 2x plus 3y integration with respect to x is minus cos 2x plus 3y into another half. Already there is a half, and phi 1y constant, so integration del x will give only x plus phi 2y, another arbitrary function added instead of arbitrary constant, because we have integrated with respect to x keeping y constant. So this simplified 1 by 4. Now integrating with this partially with respect to y, del z del y will become z, and here if we integrate with respect to y, cos 2x plus 3y integration will be sin 2x plus 3y into 1 by 3, coefficient of y is 3, and here integration of phi 1y del y, x constant taken out, integration phi 2y del y plus psi x. So this is z equal to minus 1 by 12 sin 2x plus 3y, and let us name this integration phi 1y del y as fy and integration phi 2y del y as gy, just name plus psi x. So this is required solution. Example number 3, solve del square z by del y square equal to z, given that y, when y equal to 0, z is e to the power x and del z by del y is e to the power minus x. Under this condition we have to solve this particular solution, we have to find. This time we cannot integrate directly because z is a function of x and y, its explicit form we don't know. So we have side changed and we have written like d square minus 1 z equal to 0, where d means del y. So d square will be del square y by del square by del y square. So this is a second order linear equation with constant coefficients, like ordinary second order linear equation with z and y as variables. Z is dependent, y is independent. So auxiliary equation is replacing d by m, we know m square minus 1 equal to 0, so m is plus minus 1. Therefore solution is z equal to a e to the power y plus b e to the power minus y, because m is 1 and minus 1, and instead of ab we have written ax and bx, because under this process x is assumed constant, so a and b may involve x, that's why ax bx are functions of x alone. Therefore del z by del y is e to the power y derivative e to the power y, e to the power minus y derivative is minus e to the power minus y. Now given z is e to the power x, del z del y is e to the power minus x when y 0. So putting y 0 in these two lines, we have got this line number 1 and 2, and then adding 1 and 2 and subtracting 2 from 1, we get ax equal to half e to the power x plus e to the power minus x, that is cos hyperbolic x, definition of cos hyperbolic x, and bx equal to half e to the power x minus e to the power minus x, this is definition of sin hyperbolic x. So ax bx obtained, therefore required solution is given by z equal to e to the power y cos hyperbolic x, e to the power minus y sin hyperbolic x, putting values of ax and bx. Number 4, solve del z by del x equal to plus twice yz equal to y sin x. Here also we cannot integrate directly because of presence of this z. It is a first order linear differential equation in z and x, where y is assumed constant. Assuming y constant, because derivative is with respect to x here, so y constant if we assume that this is a linear equation, first order linear differential equation with z as dependent variable. So integrating factor is, as we know from first semester, e to the power integration p del x. Instead of dx only we are writing del x, partial derivative. So p is what? Coefficient of z, 2y. 2y, but 2y is constant, so it is only e to the power 2y x. Integration del x is x, so e to the power 2xy. Solution is given by z into if equal to integration q into if del x plus phi y. Instead of arbitrary constant, here it is arbitrary function phi y, because under this process y is constant. So if is e to the power 2xy substituted, and y is constant taken out. Now this is e to the power 2yx I have written, sin x del x plus phi y, means as if e to the power ax sin bx dx, like that. So there is a standard result. E to the power ax sin bx indication is e to the power ax by s square plus b square, means 2y square plus 1 square, and this is a sin bx minus b cos bx. B is here 1, bx sin bx, and a is 2y. So this is standard result from class 12 also you have got, directly you have used. Then e to the power 2xy we have divided both sides and got this line, which is required solution. Number 5. Del square z by del x del y plus del z by del x equal to 2x, or del x of del z del y plus del z del x equal to 2x, or you can write in one bracket del x of del z del y plus z equal to 2x. Now integrate with respect to x. We get del z del y plus z equal to 2x. Integration will be x square by 2, and these 2 will be cancelled, so x square plus phi y. But integrating partially with respect to x, phi y arbitrary function of y. Now this line we cannot integrate again because of this z, but it is a linear differential equation of first order in z and y, and where x is assumed constant. So if is e to the power integration p dy. P means here coefficient of z 1, so it is integration del y dy, not del y, it is e to the power y, and solution is given by z into if, means e to the power y, equal to integration q into q is here x square plus phi y. If is e to the power y del y plus psi x. Now two integrals here, e to the power integration e to the power y is e to the power y, and this is unknown function, so let us name e to the power integration e to the power y phi y del y as just phi 1 y, and psi x is there, arbitrary function of x, and then dividing e to the power by e to the power y both sides, we get this line, which is required solution of given PDE. Example 6, 7, 8 are homework. With the knowledge of all these 5 examples as solved above, you can solve, answers are given. Next, some important terms: complete integral or complete solution, particular integral, general integral or general solution, and singular integral as applied to first order PDE. If from the first order PDE sorry, if from the first order PDE f of x, y, z, p, q equal to 0, p means del z del x, q means del z del y, we can find a relation phi of x, y, z, a, b equal to 0, which contains as many arbitrary constants as there are independent variables. Two arbitrary constants a, b, and here two independent variables x and y. That is, from which, means from this phi x, y, z, a, b equal to 0, the PDE can be formed. Then this relation phi x, y, z, a, b equal to 0 is called the complete integral or the complete solution of the PDE. Number of independent variable equal to number of arbitrary constant in the solution, then that solution, that integral is called complete integral. Now giving particular values to the arbitrary constants in the complete integral of the PDE, we get particular integral or particular solution. Next, if u and v are two functions of three variables x, y, z which are connected by an arbitrary functional relation phi of u b equal to 0, then eliminating phi, we get a PDE from of the form capital P into small p plus capital Q into small q equal to capital R, where P means del z del x, Q means del z del y. So that phi u b equal to 0 is a solution of this PDE, which is called the general integral or general solution. If phi xyz ab equal to 0 is the complete integral of a first order PDE f xyz pq equal to 0, where a and b are arbitrary constants, then eliminating a and b from phi xyz ab equal to 0 and del phi del a equal to 0, partial derivative of phi with respect to a, and del phi del b equal to 0. Suppose we get psi xyz 0, ab will be eliminated, so psi xyz new relation is 0, which is called the singular integral of the PDE f xyz pq 0. The singular integral psi xyz 0 is actually the envelope of the complete integral phi xyz ab equal to 0. Now, Lagrange's linear equation and its solution. A PDE of the form capital P into small p plus capital Q into small q equal to capital R, where small pq are as usual del z by del x and del z by del y, and capital P Q R are functions of x, y, z. And it is the standard or canonical form of a linear PDE and is known as Lagrange's linear equation. It is actually a quasi-linear equation. The general solution of this PDE number 1, Lagrange's equation, is given by phi of ub0, where phi is an arbitrary function and u means uxyz equal to c1, v means dxyz equal to c2. U is a function of xyz, v is a function of xyz. uxyz equal to c1 and dxyz equal to c2 are two independent solutions of the simultaneous ordinary differential equations dx by p equal to dy by q equal to dz by r, where at least one of u or b must contain z and c1, c2 are arbitrary constants. The equations number 4 are called Lagrange's auxiliary equations or Lagrange's subsidiary equations. So this is Lagrange's linear equation and its method of solution written here. Now let us justify by this process we get the solution. So that's why proof. Consider phi u b equal to 0, where u and b are functions of x, y, z, and at least one of u or b contains z, and also z is a function of x and y. Now differentiating this line number 1 partially with respect to x and again partially with respect to y, we get these two lines. These two lines already we have got in page number 5. So you can see that page again, already explained. Eliminating del phi del u and del phi del b from 2 and 3 and proceeding as in page number 5, we get capital P into small p plus capital Q into small q equal to capital R, where capital P, Q, R are functions of x, y, z as in page number 5. I am not repeating it, you can see. So therefore general solution of this PDE number 4 is given by phi u equal to 0. Now we proceed to find u and b. What are u and b? Already written here. U are independent solutions of this number 4. Let us check. Consider uxyz equal to c1 and bxyz equal to c2 are c2, where c1 and c2 are arbitrary constants. Therefore du equal to 0, db equal to 0. Du means total differential of u, total differential of b, because I said constant, so total differential 0. And in first semester we know du means del u by del x into dx plus del u by del y into dy plus del u by del z into dz equal to 0, because u is a function of x, y, z. Similarly for db equal to 0 gives this number 6. Now from this 5 and 6 by cross multiplication we get dx by dy by dz by dx by what? Del u del y into del b del z minus del u del z into del b del y. You know cross multiplication, dy by del u del z into del b del x minus del u del x into del b del z, dz by again del u del x into del b del y minus del u del y into del b del x. But these are actually p, q, r as in page number 5 we have already got. So dx by p equal to dy by q equal to dz by r. Therefore u equal to c1 and b equal to c2 are solutions of 7 which are independent. Independent means b is not a constant multiple of u, or u is not a constant multiple of b. U by b is not constant. Now working rule for solving Lagrange's linear equation pp plus qq equal to 1. Step 1, the equation may not be directly in this form. So first work will be put the given linear or quasi-linear PDE in the form pp plus qq equal to r. Then write down Lagrange's auxiliary equation as dx by p equal to dy by q equal to dz by r. Now solve this number 2 using well-known methods, that is using multipliers or otherwise, considering two ratios like that, to find two independent solutions uxyz equal to c1 and vxyz equal to c2. The general solution or general integral of the PDE, Lagrange's linear PDE number 1, is then written in one of the following three equivalent forms: phi u b equal to 0, or u equal to phi b, or v equal to phi u, where phi is an arbitrary functions. Now let us solve some problems. Number 1. Solve the PDE x p plus y q equal to 3z. P means del z del x, q means del z del y. So here it is obviously a Lagrange's linear PDE. Here p is x, q is y, r is 3z. Therefore Lagrange's subsidiary equations or auxiliary equations are dx by p equal to dy by q equal to dz by r, or dx by x equal to dy by y equal to dz by 3z. Now from first two ratios we get dx by x equal to dy by y, and from second two ratios we get dy by y equal to dz by 3z, or you can take 3 here, 3 dy by y equal to dz by z. Now readily we can integrate these differential equations, ordinary differential equations. So integrating we get dx by x integration is log x, dy by integration is log y, plus instead of c1 we have used log c1, and here 3 dy by y integration is 3 log y, dz by z is integration is log z, and instead of c2 we have written log c2. So side changing, log x minus log y means log x by y equal to log c1, and here 3 log y means log y cube minus log z means divided by z, so log c2. That is x by y equal to c1 and y cube by z equal to c2. That is u equal to c1 and b equal to c2. Here u is x by y, b is y cube by z. Therefore general solution of the given PDE is phi of u b equal to 0. I usually write phi of u b 0. You can write b equal to phi u or u equal to phi b, or phi of x by y comma y cube by z 0. Solve the PDE. Example number 2. Solve the PDE y z minus yp plus x minus zq equal to y minus x. Here obviously it is a Lagrange's linear equation or Lagrange's linear PDE. Here p is z minus y, q is x minus z, r is y minus x. Now Lagrange's subsidiary equations are dx by p equal to dy by q equal to dz by z. That is dx by z minus y, dy by x minus z, dz by y minus x. Now here p q r, if I add p q r I get 0. That means 1 into p plus 1 into q plus 1 into r equal to 0. So taking multipliers as 1, 1, 1, we see that 1 into p means here y minus z, 1 into q means x minus z, 1 into q, r means y minus x equal to 0. That means 1p plus 1q plus 1r 0 means what? 1 dx plus 1 dy plus 1 dz should be 0 because they are proportional. Therefore dx plus dy plus dz 0, and therefore integrating readily we get x plus y plus z equal to c1. That is u equal to c1. U we have got. Again taking multipliers as x, y, z, we see that if we multiply this pqr by x, y, z respectively and add, what we get? X, z minus y plus y, x minus z plus z, y minus x equal to 0. You can check. That means what? Numerators were dx, dy, dz. So it will be x dx plus y dy plus z dz also 0. Therefore integrating we get x square by 2, y square by 2, z square by 2 equal to c2 by 2. Here I have written c2 by 2 so that these two gets cancelled. Answer will be nice. So x square plus y square plus z square equal to c2. That is b equal to c2. Therefore general solution of PDE number 1 is given by phi of u b 0. That is phi of x plus y plus z comma x square plus y square plus z square equal to 0. Number 3. Solve x into y minus z p plus y into z minus x q equal to z into x minus y. It is a Lagrange's linear equation. Now just hint is given. Take multiplier as 1, 1, 1. You will get dx plus dy plus dz 0. So integrating we will get x plus y plus z equal to c1. Again taking multiplier as 1 by x, 1 by y, 1 by z. You will get again 0 means 1 by x dx plus 1 by y dy plus 1 by z dz will be 0 means integrating you will get log x plus log y plus log z equal to log c2. That will give you x y z equal to c2 means b equal to c2. So solution is this. Solve number 4, p minus q equal to log x plus y. So here also hint is given. From first two ratios of subsidiary equation you will get x plus y equal to c1. From first and third ratio you will get this, but to get this you are to use x plus y equal to c1, otherwise you will not be able to integrate. You will see when solving. Number 5, p 10x plus q 10y equal to 10z. Answer is given, nothing mentioned, you will do yourself. So some examples solved, some are left as exercise, and theories discussed nicely. PDF is also very clear, and more examples, special type of examples we shall discuss in the third lecture. Thank you for today.